How do we factor polynomials with a degree higher than 2, such as these two polynomials here? The first important rule we need to understand is the total number of real or complex solutions to a polynomial is equal to the highest power. So we have a look at these two polynomials here. How many potential solutions would each equation have? So we look at the highest exponent or power in each polynomial, and we see that the first equation has 3 solutions and the second has 5 solutions. And we don't know yet whether these solutions are real solutions or complex solutions. So let's start with this polynomial. We've got 4y cubed minus 9y equals 0. Now, because the highest exponent is 3, we would expect to get 3 solutions. But what could our first step be in solving for y? Well, we have 2 terms here, and we can factor out the greatest common factor. And remember, the greatest common factor is the largest positive integer, or power, that divides each term evenly without leaving a remainder. So for our coefficients 4 and 9, the greatest common factor is 1. So we can now place a 1 outside of our brackets here. Now, with our algebraic expressions y cubed and y to the power of 1, what's the highest power of y you think would divide evenly into both expressions? Well, if we divide y to the power of 1 by any power of y with a higher power than 1, then we'd end up with a fraction. In other words, our greatest common factor here can only be y to the power of 1. And we can place this outside of our brackets. Inside our brackets, we are left with 4y squared minus 9. Notice now that one of our factors is the difference of squares, and therefore we can factor this further. And this leaves us with 2y plus 3 for one factor and 2y minus 3 for the second factor. We can implement the zero product property to find our 3 values here. So we have y equals 0, y equals minus 3 over 2, and y equals 3 over 2. Okay, with our next example, we have 4 terms in the polynomial, which means we can solve by grouping. Now, grouping involves factoring out the first 2 terms and then factoring the last 2 terms. So this factoring procedure works exactly the same as in the first example. In other words, we need to find the greatest common factor for the coefficients and the algebraic variables. So how would you factor out the first 2 terms here? We start with the coefficients 1 and 3, and the greatest common factor is 1. For the algebraic terms, x cubed and x squared, the greatest common factor is the lowest power, and we end up with x plus 3 in the first bracket. So let's do the same with the last 2 terms in the second grouping. The greatest common factor of 25 and 75 is 25. And for the x terms, the greatest common factor is x to the power of 0. So we're left with x plus 3 in this bracket as well. And the fact that the values in the brackets are identical means we can continue to solve this problem. So our factors are x squared minus 25, which you notice again is a difference of squares, and x plus 3. So again, we can use the zero product property here directly, or we can factor the difference of squares further. And we've got 2 different methods here. So the first method would be applying the zero product property directly, and the second method, we're factoring out the difference of squares. And our x values are 5, minus 5, and minus 3. So the last example may or may not catch you out. We have 5x cubed minus 2x squared plus 45x minus 18. Now what's the first thing we notice here? Well, we've got 4 terms again, so we can attempt to solve this problem by grouping. So let's start with the first group again, and we need to factor out the greatest common factor for the coefficients and for the x terms. So the coefficients are 5 and 2, and the greatest common factor here is 1. And for the x terms, we have x squared as the greatest common factor. Let's do the same for the second grouping. The greatest common factor for 45 and 18 is 9. For the x terms, again we've got x to the power of 0, which is equal to 1. And we end up with x squared plus 9 and 5x minus 2. Now this factor here is not the difference of squares. In fact, this polynomial has no real solutions, but we can apply the zero product property and see that we get a negative root. So what do we do here? So our x value here is plus or minus the square root of positive 9 multiplied by the square root of negative 1. And the square root of negative 1 is our imaginary number. So we end up with plus or minus 3i for 2 values of x. And for our final value of x, we just solve in the regular way, giving us x is equal to 2 over 5.